Hello everyone, welcome back to my channel. If you are new to the channel, please subscribe. Today we are going to see a forward bias characteristic of a diode. We can call it as a IV characteristic of a diode. So here it is a forward bias characteristic diode's circuit diagram. You can see here is a 2 volt battery. We can say is a DC volt battery or a DC power supply. Resistance Rs, this is a current limiting resistance, so it will limit the current that is flowing through this diode. This is a diode where the anode terminal of the diode is connected to positive part of the battery and the cathode terminal of the part is connected to negative of the battery, make this circuit to be as a forward biased. And here is a current meter that is going to measure the current when the voltage is vary from 0 to 2 volt in this particular diode. So what we can see when we done the experiment on the diode, a forward bias characteristic experiment, you can see there will be a voltage at x-axis that is increasing from 0 to 2 volt, and we are getting current at y-axis in milliamps. So where you get a graph that is starting from like 0, and at from A to B the curve will be rapidly increases, that we can say current is rapidly increases. So you can see the current is increases at a point called as a knee voltage. So this is the term, it is available in the forward bias characteristic of a diode. So knee voltage is one where the current start increase rapidly, and that is shown in this diagram. So biasing voltage increases typically for silicon diode it is 0.7 volt, and for germanium diode it is 0.3 volt. So after that knee voltage the current is rapidly increasing. So using Ohm's law we can calculate the resistance of a diode. So for below 0.7 volt at point A, which is to be calculated, and it is approximately 5 to 25 ohms, and above zero point 0.7 volt at point B, this is to be again 1 to 3 ohm. So this is known as the dynamic resistance value of a rectifier diode. So we can calculate using the P spice how this dynamic resistance, knee voltage, and the forward bias diode IV characteristic can be drawn. So here, but why the dynamic resistance is very important, because it is useful to select proper series current limiting resistor to operate diode in safety current and voltage ranges. So we can see here this resistance Rs that will be selected according to these two resistance at A and resistance at B. So we can see by just seeing that particular backslide, you have seen that the resistance is very low. So we don't need to take the resistance Rs to be as having very high value. So we can have the resistance of the Rs should be very low. So let's look at how this simulation of the circuit is drawn in case of a PSpice software. So here is a PSpice software. I request you to see this video in full HD, then and then only you can see the small font, or we can say the small menus inside this software. So what I am going to do, I am going to draw a diagram so where we required. So for this purpose what we need a draw in that get new part, or there is an option called Control G, or there is a shortcut here, you can take the new part in here, control by this draw, then get new part. From that you can take the components, or there is an option where we can take the shortcut called Control G, or in case of this there is a button, or we can say shortcut, that is a get new part. So what we need to take, we need to take VDC. So I am taking VDC. So I am saying just place, it will be attached to my this pointer. So I am going to click over here. What we need again, a diode. So I'm not going to take only D because it will show some error. I will take a diode which has some sort of name that is called a model 4002. So So I'm going to place it again in here. Then I need a resistance, so I'm pressing just R. We can take simple R as well. I'm placing in here, and then the most important part is called a ground, because in case of this socket we required always a ground. So I'm placing close, I'm placing it in here. Okay, so it is done. It is stick to my just pointer. I'm going to press escape, so it will be gone. I'm going to make this as zoom to fit page, so it will be fit to the page. So you look at here, this is zoom to the fit page. Then I'm going to take this VDC, place over here. Then what we need resistor over here, we need diode over here, and then the ground terminal over here. I'm going to again fit page. Control W is the option to connect VCC's plus terminal to resistance R1's one terminal. R1's one terminal is to be connected to diode D1. Anode, cathode is connected. This cathode is connected to be ground. This ground is connected to negative of the battery. Okay. Now I am going to place the voltage to be as maximum of 2 volt. Okay. So done with the circuit diagram. What we need to save it first of all. So file, can save it. So saving is also very important. I am going to make folder known as forward bias diode characteristics. So naming it means it will be easily found, or it will be easily available in your computer. Then analysis, electrical rule check for any errors if they are available. You can see in a like raw file view message, or pressing F10, you will have one message, and that has zero error, zero warning. Netlist is completed. Then we are going for the next part, that is called as a setup. So where we are going to take a DC setup, as we are going to vary the voltage source. So what is the name of that voltage source? Just me take a look at, this is V1. So I'm going to take a DC sweep voltage source as V1. We are going to start that V1 with 0 volt, will having an ending value called 2 volt, and it should be start with increment with 0.01. Okay, you can give the voltage over here also. Okay, I'm going to press OK in here, close. Okay, if we need to find out where is the current direction, we can place voltage marker over here, so that the graph will be drawn according to this particular part. So analysis, simulate, there are no error, no warning, all things are good. We are going to see the simulation window. You can see here. So we are done. Analysis, then simulate. We are going to simulate it. We are having a blank, we can call it as window. Then we are going to add the trace. So trace, add trace, we have to plot the current. I am going to press ID1. Okay, so this will be the current. Now you are seeing the graph. The graph is from starting from 0 volt and ends toward 2 volt. So if we double click over here, we can limit the function, supposed to be 0.5 volt. I'm saying okay. You can look at here up to the 500 millivolt. The graph is shown in here, and you will see that this is the graph. Volt or 200 millivolt onwards, the graph is slightly goes in the positive direction, and you are seeing the voltage over here. It is a 40 microampere, 80 microampere, and so on. So if you need to find out the new voltage, just take this particular graph at the back. We can draw the line over here, and we can see that at 300 millivolt this will be the knee voltage. So this is a germanium diode, so that's why we are getting approximately equal to 300 millivolt or 0.3 volt. Okay, so by taking this trace you can put the cursor over here. So if I put the cursor over here at this point, so I'm getting the A1 and A2. So you can see A1 is 370 millivolt and A2, no, it is 14.62. So this is 14 microampere, this is 370 millivolt. So from that you can calculate a dynamic resistance value R. Now we have to go to the point, suppose this point, we can say this point is a B. So we have 475 millivolt is the voltage at that point, and 53 microampere is the current at that point. So you can see from these two values you can calculate the value of the resistance, and then the dynamic resistance value is to be calculated. So this is the way you can do the forward bias characteristic of a diode in a PSpice software. Now, in case of a reverse bias characteristic of a diode, you can see here the voltage is of 10 volt and the negative terminal is connected to anode and the positive terminal is connected to cathode. The resistance R is the same as it is, and you are getting the current. So you can see the current will flow from positive part of the battery or positive terminal of the battery to this ammetter's positive terminal, then cathode, anode towards the negative terminal of the battery. So you can see the current is flowing, that is in a reverse direction. So if we plot the graph of it, you can see here the voltage it at the y-axis and the current is at the x-axis. So this is actually the third quadrant of the our graph. Now a very few or almost zero current will flow through it. So this will be a very small amount of current, and that is due to the minority carriers available in the PN junction diode. So that's why we are getting a current that is due to the minority carrier, and that's why it is called as a saturation current. So this is independent of the applied reverse voltage. So whatsoever the reverse voltage is there, the current will slowly increases and it will remain as it is. So when the reverse bias voltage is increased further, the electron on the surface of the crystal move towards the positive terminal of the battery. At the higher level, these electrons will have high velocity, which can dislodge valence from the crystal structure. And then finally, what will happening? So beyond this voltage, the current will start rapidly increasing in the negative direction. That particular part is called as a breakdown. So there are two types of breakdown available in the uh, diode. One is called Zener breakdown and another one is called avalanche breakdown. So we'll see how the Zener and avalanche breakdown happens inside the reverse bias of the diode. So we are going to see just the reverse bias characteristic of the diode in a PSpice software. So you can see here at the breakdown voltage, large reverse current flows and it is in the negative direction. So you can see the voltage at which the large reverse current flows inside a diode, that voltage is called as breakdown voltage. So this breakdown voltage is nothing but a safest voltage that should be applied to a diode in a reverse direction. So this breakdown voltage should be seen in your data sheet, and beyond that there should be no voltage. We have to apply the voltage in between 0 towards this breakdown voltage. So this is the safety purpose. Beyond it, the large reverse current will flow, or we can say there will be a breakdown. That may be a Zener or that may be a avalanche breakdown. So to see the reverse bias characteristic of a diode, just change the polarity of the supply to minus 10 volts suppose, and then we are going to have analysis, electrical rule check analysis. In that setup we have to go DC switch, and we should start with the 0 and it will be end on like minus 10 volt and with the increment of 0.1. I'm saying okay, close, analysis, and then simulate. We are going to see the graph. Okay, so in that the voltage is from like 0 towards the minus 10. We have to add the trace. So trace, add trace, id1 we have to check the current only. So this is the current. So you can see this is a third quadrant. Actually you can see this is a 0 and this is a 0. So current that is starting from this point and it will come towards this point, and then it will be independent of the applied voltages. So whatsoever the voltage, maybe -1, -2, -3, -4 up to -10, the voltage will remain as it is. So this is called a reverse bias characteristic of a simple PN junction diode. Hope you understand the forward and reverse bias characteristic of a diode. Thank you for watching my video. If you are new in the video, please subscribe channel. Thank you.